Today we are going to learn how to extract persons out of an image. So in order to do that, we're going to use the Unet model, the Unet architecture. So basically we are going to build a model and we will learn this model to extract or create masks of person out of images. And it all will be based on, of course, the relevant database. For example, this is a person in an image, and we are going to create a mask that helps us to extract the person out of this image. And of course, you are most welcome to subscribe to my channel and look for other TensorFlow and deep learning tutorials. So what is a Unet architecture? Okay, let's dive into a Unet architecture. A Unet architecture is a type of deep neural networks that commonly used for image segmentation tasks. And image segmentation is a process of diving an image into different parts and assigning a label to each detected part. This is useful in various applications like medical image analysis, where you might want to identify and classify different structures within an image, such as organs and tumor. As you can see, this is a U shape. The Unet architecture gets its name from its shape, which looks like U when visualize it as a diagram. As you can see, it consists two parts. There is the left part and there is the right part. Encoder is the part on the left side of the U shape. It takes the input image and gradually reduces its spatial dimensions while capturing important features. This helps the network learn high-level representations of the input image. The encoder follows a typical architecture of convolutional networks. As you can see, this is, for example, has 64 filters, and this one has 128, and this one 256. Basically, it consists of repeated applications of two 3x3 convolutions, each followed by a rectified linear unit, a ReLU, and a 2x2 max pooling. For example, this red cross, a 2x2 max pooling operation with a stride 2 for the downsampling. The decoder, this part is on the right side of the U shape. It takes the feature learned by the encoder and gradually increase the spatial dimensions back to the original size of the input image. The decoder's job is to generate segmentation map that assigns a label to each pixel, indicating which part of the image it belongs to. So the key feature of the Unet architecture is its use of skip connections. You can see here, for example, is the skips connections. These connections allow information from the encoder to directly reach corresponding layer in the decoder. This helps the network combine both high-level and low-level features, which can lead to more accuracy in the segmentation results. Okay, so let's start with part one of this Unet tutorial. As I said earlier, it will be based on the TensorFlow, Keras, and Python. So in this section, we will download the dataset and prepare it for training. So let's start with the Kaggle website, and we will look for person segmentation dataset. So as you can see, this is the third one in the list, and we can do a deep dive of the images inside this dataset. You can see that are divided to images and to masks. I will explain about it more later, but as for now, let's download the full file, the full zip file from the person segmentation dataset and extract it on your local folders. So as you can see, we extract the zip file, and you can see there are many images of persons, many types of images, And we also have a mask folder, but as for now everything seems black, but we'll explain it later on. Moreover, we have a train.txt file that has the names of all the images, and we have it for train and for validation as well. So let's start coding. The first Python program would be step number 1. We call it loaddata.py. To start, we'll be using a dataset from Keras that we focused earlier on the person segmentation. I will leave, you can find the link for the dataset here in the first row. Next, we import the necessary libraries, including OpenCV for image processing, and NumPy and Pandas for data manipulation. Next, we set the height and the width of our images. So since we don't know what is the dimensions of each image, we are going to resize it to our own height and width. And next, we define the path for the dataset folder and files. 1 second, now we are defining the path. We will have a separate path for the images and the mask. This will be also as well as for path for the training and the validation files. I didn't mention it, but we also created the lists for all these types of for images and masks, one for the training and one for the validation. The datasets include text files for train, test, and validation, so it will be more convenient to create this train file. So we will use the train.txt file in order to load the images. It will be more easy to read this file using the pandas, and then we can loop through the name of the images and load them into our 4 lists. Okay, so we are almost done. We have a one file for the train and the other file for the validation. I think it's named, yes, it's val.txt, so we'll fix it and continue. Now let's create a data frame, and we will use the read_csv function from pandas to load the train.txt file. As we saw earlier, it doesn't have any headers, so the first row is the first image, so we use the header none, and this files list will be all the names of this txt file. And as the next step, we began by loading an example image and its corresponding mask. So we will use the imread function in order to load this image from the images folder. Okay, let's copy the name of one of the images, this one for example, and copy the full path. And of course it's a color image. This is the default, by the way. Next, we resize the image to our specific dimensions and display it using OpenCV. And we will use the imshow file, the imshow function in order to display the image. And the wait key is waiting for a key to press, and let's run it. Okay, this is the image after being resized to 256 by 256. Next, we would like to display one of the masks. Earlier we saw that all the images of the mask are black, so we would like to see what is inside those masks. So let's take the corresponding mask for this image. Of course it's on the mask folder, and we have to change it to PNG since the masks are PNG files and not JPEG. And if we display the image, it would be black, of course. So let's resize the image to 16 by 16 and let's print it. It will be easier to see it on the log. So let's resize this to a very small image and let's see the result. As you can see, there are 0 and 1s, and please notice that the 1s display indicates where is the person in the image. So this gives us a sense of what should we do next. 0 is the background and 1 is basically the human. So in order to display the mask side by side to our image, let's change the values. All the backgrounds will stay 0 and all the ones we convert it to 255. That means a white value. So once again we are resizing the mask to the same values, 256 by 256, but we are multiply it by 255, and now you can see this is the image and this is the corresponding mask. Cool. So let's continue to the next step. Moving on to the training data, we load a list of the file names from the training file, and next we are going to iterate through these files, loading each image and each mask, resize them, and then we will normalize the image to a values between 0 and 1, so it will be ready for our model. And we store these images inside an image list and a mask list. I hope I'm understood. So we divide it to several steps. As the first step, just to see they are looping inside the list of images. As you can see, it works correctly. I ran it very fast, so believe me that it loops inside all the images. And next we are going to do what we have done for a separated image. That means that we are going to load the image and convert the image to our dimension, and then add it to our images list and mask list. We are also make sure that the type will be float 32. It will be more easier for our model, and we also make sure that the type of the mask would be integer, since it should be 0 or 1. As you can see now, it's the part of the mask. Of course it's a grayscale since it's a black and white. Resize it to the same dimensions, and just copy paste the name of the list and then add it to the mask list. Then after looping through the images, we would convert the list to a NumPy array. It would be easier to save those images, and it would be more easier for our model to deal with the NumPy array. So The last two lines is convert the list to a numpy array, and we also double checking that the mask are in integer type. So we are convert the results to integer. Next, let's print the shapes of the images and the masks to see that everything is okay after loading those images. Let's also print the type of the mask just to see that it is an integer. It's optional, it's just to debug our code. As you can see, we have more than 5,000 images that are divided to two lists, one for the images with 3 channels, the 3 colors, and one for the masks. Similarly, for validation data, we follow the same procedure, loading images and masks and storing them in separated lists, and these lists are then converted to numpy array. So basically it's the same process that we have done for the train images and mask. We are repeating it for the validation data as well. So basically it's a copy paste. We are just fixing the relevant text and variables. Finally, we save all the training and validation data as numpy array in a specific path and of course specific files, so we can use it in step number 3 when we will start training our model. So as you can see, we are using the save function of a numpy array, and for each of the files we have the corresponding numpy array. Okay, let's run it. It's printing all the files through the loops, and we have an error. Okay, we have to replace the right mask, the right array. We should be mask validation images. So let's run it again. Okay, it's saving the data. Now it seems okay. In the next section, we will move on to building our Unet model. So the unit architecture is composed of encoder and decoder, which allows for accurate image segmentation. So we'll define a convolutional block and a function to build the entire unit model. So first we import the necessary TensorFlow and Keras components. We will use layers like conv 2D, batch normalization, activation, max pull in 2D, and upsample in 2D, and concatenate. We will use those functions from the Keras environment, Keras envelope. And we will start by defining the conv_block function. And this function takes in an input tensor x and the number of filters, which call it num_filters, and it performs two consecutive convolutional layers, each followed by batch normalization and ReLU activation. And this block helps us capture hierarchical feature in the input data. Once again, we will see the unit architecture, and each layer has two convolutional layers inside it. I explained it earlier on the preface of our tutorial. Moving on to the build model function, we pass the input shape to create an input layer. We defined a list number of filters to specify the number of filters for each layer in the encoder and the decoder. As you can see, I'm using different values, 16, 32, 48 and 64 instead of the original value, since it requires more GPU memory, but as for our tutorial it would be good enough. Then we defined our input function and use our required shape. Then in the encoder section, we iterate through the number of filter, and the number of filter lists. For each filter count, we apply the conv_block function that we set earlier. So we apply this conv_block function to the input tensor x, saving a reference to the tensor in the skip_x list, and we also perform a max pooling to downsample the spatial dimensions. After the encoding, we have the bridge, where we apply another convolution block with 128 filters to capture the context information. Once again, in the original unit architecture, it's 1024. And then moving to the decoder section, we reverse the num_filter list and the skip_x list. For each filter count, we use the upsampling 2D function to increase the spatial dimensions. Then concatenate the upsample tensor with the corresponding tensor from the skip_list, and then apply the conv_block. So basically it's the opposite way from the decoder. And finally, we add an output layer with a single channel using the conv2d function, and apply a sigmoid activation for a binary classification. And I think the model architecture is completed. Okay, that is for part 2. In the next section, we will dive into training the unit model using our prepared dataset. Okay, let's start. Once again, we create another Python program. Let's call it step 3 train.py. Of course, all the code will be in my GitHub repo. We start by loading the saved training and validation data that we prepared earlier. This includes the images and their corresponding masks for both training and validation sets. So simply we are copy and paste the names of the files and using the load function in order to load it into to NumPy variables. The data shapes are then printed to ensure everything loaded correctly. And let's run it. As you can see, we have a four NumPy array. Everything look good. Let's continue. We proceed to build the model by importing the necessary libraries. We will import the TensorFlow, and also we will import we called the build model function we defined earlier to create our unit model. And we also import more relevant TensorFlow and Keras function. We explain it in the next phase. And we will print the model summary to display its architecture, once again just for validation. We defined a shape and the learning rate and how many epochs. It would be 50, and the bed size would be it would be 8. We will fix it in a few seconds. Yes, let's fix it now. Let's run. We are expecting to see the summary of our unit model. Just to double check. Yes, everything seems okay. Let's continue. Next, we are going to compile the model using the Adam optimizer. And we, of course, since it's a binary, we are basically looking for a 0 and 1. So we are basically looking for a mask. So it's a binary question. So we'll use the binary cross entropy loss function. And the matrix will be accuracy. Next, we calculate the number of steps per epochs and the validation steps. It will help us in the efficiency using the data during the training. Basically, we are dividing the number of images by the bed size, the number of the trained images, and the number of the validation images. The name of the saved model would be human, let's call it a human unit.h5. we're expecting to see this file after the training. And callbacks are employed to enhance training. The model checkpoint function saves the best model during the training. The reduced learning rate on plateau reduces the learning rate if the validation loss goes to a plateau. And the early stopping stops the training if the validation loss doesn't improve after a certain number of epochs. So I don't think that we are expecting to see the whole 50 epochs. Probably we'll stop earlier. Let's define our patience to 5. That means that if in 5 epochs there was no improvement, then the model will stop training. Finally, we feed the model to the training data using the feed function. We pass in the training images and the masks. We also pass the validation data, the batch size, and our defined callbacks. And after the training model starts, you can monitor the progress through the printed log. As you can see, we are passing all the relevant variables and arguments that we defined earlier. The last one is the callbacks. And I think we can run it. Okay, the model start training. I will run it through a fast forward process. And let's wait a few more seconds until it finishes and we can see the result. During the training, you can see that each time that the validation loss is better from the previous epochs, the model is being saved to our human unit.h5 files. And you can also look at the validation accuracy. It's about 0.9. So it's a very good validation accuracy. Basically, the model performs very well. The training performs very well. As you can see now, the learning rate was reduced. So that means that also this function works very good. And it was early stop after 25 epochs. Now let's find our file in the folder. As you can see, this is the saved model, and now we are ready to test our model on a new fresh image. So this would be our image. Let's create the last Python program. Let's call it test the model. So first of all, let's import the relevant Python libraries. We need, of course, NumPy and TensorFlow and OpenCV in order to display and resize the image. And then let's copy the name of our saved model, and we will use the TensorFlow load model function. So we began with loading this trained model and print the model summary just to provide an overview on its architecture and see that it was saved and loaded correctly. Next, we specify the height and the width we want our input image to be resized to. We then load an image that we want to test the model on. This would be our image, and we will do the same process. The image would be resized and normalized between values of 0 and 1. So let's wait a few more seconds. Now we are loading our test image. The next step, we are resizing the image to our required dimension, 256 by 256. And then we are normalize the data between 0 and 1. Before passing the image to the model, we need to expand its dimensions to match it to our model input shape. And the final step is running the prediction with our converted image. And let's print the result. We have to fix the slashes, the directions of the slashes for our image. Let's run it. And as you can see, we got a, let's call it a bunch of numbers, and we would like to understand those numbers. So instead of print the numbers, let's print the shape of the results. Once again, let's run it. And as you can see, we have a shape of a 256 by 256 by 1. So basically, the result is a mask. The resulting mask is then processed and converted into a binary mask. What does it mean? Values in this mask that are greater than 0.5 would be set to a white color. That means will be set to 255, while values less than or equals to 0.5 will be set to 0. That means it would be black. Then if we would like to visualize the results, we will get the white area would be the person and the black area would be the background. And the final step would be resizing again the image, basically resizing our predicted mask image according to our original image. So we are getting the width and the height from our loaded original image, and then we will use the OpenCV library that has the resize function in order to make our predicted area in the same size of our original image area. So please follow this last step, and then we will be ready to display our mask. Okay, so now we display the original image. That means, so it's not original, the test image, and next to it our predicted mask image. And I think we done. And we can also use the I'm right function from the OpenCV library in order to save our mask to our local disk, to our local folder. Let's wait a few more seconds for the results. Cool. On the left side is the original image. This is the mask image. We can put one on each other to see both images. I hope you enjoyed this tutorial. You're most welcome to subscribe. Bye bye.